Welcome folks, a video today on two new concepts called column and row space of a matrix. So we'll start off with talking about the column space of a matrix, see how it's related to a linear system of equations. We'll talk about taking the definition of a column space spanned by original columns and paring that down. We'll relate that back to the column space of a non-singular matrix. It turns out, as you might expect, we have a new addition to our theorem of non-singular matrix equivalencies. And then we'll close with a short discussion of a related but slightly different item called the row space. Okay, so here's the definition. If A is an M by N matrix, here our columns will be denoted A1, A2 out to AN. Then the column space of A is all linear combinations of the columns of A. Okay, so we can think about it as a span of a set of vectors containing A1, A2 out to AN. Okay, a couple quick observations here. When A is an M by N matrix, then each column of A has M components. So we say that A sub I is an element of the column space of an element of the vector space of column vectors with M elements. Okay, so that's sort of an important distinction, this idea that each column of A as a vector is an element of Cm, so therefore the column space is a subset of Cm. So here's an example, the coefficient matrix associated with archetypes D and E. We'll go ahead and think about the column space of the matrix A. So here, to think about whether this element B is an element of the column space of the matrix A, well, can we write B as a linear combination of the columns of A? It turns out that yes, we can in this case, right? The corresponding linear system is consistent. So there is an X, and it looks like there should be an A4 here, such that B is x1a1 plus x2a2 plus x3a3 plus x4a4. Right? That's what it means for the linear system to be consistent. So we see that B can be written as a linear combination of the columns of A. Here we say yes, B is an element of the column space. Now if we can find elements that are in the column space, it turns out we can also find elements that are not. Here's an example. This vector C, as it turns out, is not in the column space of A. And again, to determine that, what we do is have a look at the associated linear system where A is the coefficient matrix and C is the vector of constants. We find that that linear system is inconsistent. In other words, there is no value x such that C is equal to x1a1 plus x2a2 plus x3a3 plus x4a4. So we see that C is not an element of the column space of A. Clearly I have some cut and paste problems here. Sorry about that. In any case, that check is always true for column space, right? If a vector B, we say that a vector B is in the column space of A if and only if the corresponding linear system with coefficient matrix A and vector of constants B is consistent. Okay, by definition, B is in the column space of A if and only if B is a linear combination of the columns of A. Right, we know that is true if and only if B is equal to A times X, right? This is matrix vector multiplication from earlier in this chapter. And we now know that's true if and only if the linear system AB is consistent. So here's the take-home message. To address whether B is in the column space of A, we'll go ahead and have a look at the associated linear system with vector of constant B and matrix of coefficients A. Okay, a couple equivalent statements here for alternate definitions of the column space. Sometimes we write it as the set of all y, such that y is equal to ax, or sometimes we just express it as the set of all ax. Okay, column space. So here are a couple problems for you to work on. Go ahead and have a look at whether the vector v and the vector w is in the column space of this matrix A. And again, the way we do that is by examining the associated linear system. Okay, let's go ahead and have a look at the column space spanned by the original columns. We'll start with an example. Here's a sort of messy matrix, a matrix with 5 rows and 7 columns, a 5 by 7 matrix A. And we can identify this column space in 2 ways. First, we can identify it by the definition. Okay, by definition, the column space of A is the span of the set of vectors where those vectors are exactly the columns of A. Now, on the other hand, we know that 7 vectors from C5 are linearly dependent, so we can cast some out. Okay, we know how to do this too. We start with the matrix A, we row reduce, row reduce, row reduce, and then we go back to the original set of vectors and keep the columns corresponding to the pivots in the row reduce echelon form. Okay, essentially we're applying theorem BS to the set of vectors A1 out to A7. Okay, so we do that and we find that the pivot columns in the associated row reduce echelon form are 1, 3, 4, and 5. So a better representation of the column space is the span of the set of vectors containing the first, third, fourth, and fifth columns of A. Now you might imagine we can always do this, right? We can always cast out vectors, and when we say always, we mean a theorem. So here's the theorem. Suppose that we have a matrix A with n columns. B is a row equivalent matrix in reduced row echelon form with R pivot columns. We'll go ahead and partition those pivot columns by D1 out to DR. If we go back to that set of vectors containing the columns of A and keep the ones corresponding to the pivot columns, then that set is linearly independent, and the span of that set is the column space of the matrix A. Okay, so again, this is sort of theorem BS applied specifically to the column space. Okay, so I'll let you play with this example a little bit on a worksheet. The coefficient matrix associated with archetype D we've seen before has row reduced echelon form given here. If we applied theorem BCS to this particular example, then we would keep the first and second columns of the matrix A, and those would be the linearly independent set such that the span of that set is the column space of A. Now I'll just have you go ahead and verify this, but as it turns out, if we try to find alphas, alpha 1 and alpha 2, such that this vector 2, 3, 2 is a linear combination of those alphas, we know that there are no such alphas, and we can show that this linear system is inconsistent. Okay, on the other hand, if we have a look at that vector B that is in the column space, that vector B, 8, minus 12, 4, does have a representation in terms of alphas. And we can pretty quickly see that it has to be alpha 1 equal to 4, alpha 2 equal to 0. Okay, so once again, using a linearly independent set that spans a column space gives us a unique representation of an element of that column space in terms of those vectors in the set. This is sort of becoming a theme, and we're going to explore this more as we go along. Okay, let's go ahead and talk about the column space of a non-singular matrix. There's sort of a similar idea here. We'll start with the singular coefficient matrix that's associated with archetype A. We know that that singular matrix reduces to this reduced row echelon form. We can apply theorem BCS to this matrix. If we do that, we would keep the first and second column of the matrix A as the set T, this linearly independent, that has span equal to the column space. So I'm here today to tell you that the vector 1, 3, 2 is not an element of the column space. You can try. The way we would do that, of course, is cooking up a linear system, trying to write V as a combination of the vectors from T. That linear system, of course, is inconsistent. The take-home message here is that although the column space is a subset of C3, the column space is not equal to all of C3, right? There's an element in C3, for instance, this element V, that's not in the column space, so there are missing elements here. Okay, on the other hand, with the coefficient matrix B associated with the non-singular coefficient matrix B associated with archetype B, we know that the linear system has a unique solution for all B and C3. Okay, since that linear system always has a unique solution, that is, the linear system is consistent, we know that B is always in the column space. Right, of course, if we pick any element of B that's in C3, we see it's in the column space. Of course, any element of the column space is in C3. By set equality, therefore, we see that the column space of B is equal to C3. Now, this happens to be a characteristic of all non-singular matrices. There's a theorem. The theorem is that if A is size n, then A is non-singular if and only if the column space of A is equal to all of Cn. Okay, I'll go ahead and state this theorem without proof, but the proof is sort of similar to what we just did, right? We show that any element in Cn can be written as an element of the column space of A for a non-singular matrix, and then we show the converse as well. And this gives us another addition to our non-singular matrix equivalency theorem. Okay, so here's that new equivalency. A is non-singular if and only if the column space of A is equal to Cn. Okay, let's go ahead and talk about row space of a matrix. Slightly different. Here's the definition. Given a matrix A, the row space of A is the column space of A transpose. Okay, I'll hit you with that again. The row space of a matrix A is the column space of its transpose. Okay, since we know how to find column space, we know how to find row space too. Okay, I'll point out that when A is m by n, of course the transpose is n by m. So we see that the column space of the transpose is in Cn, so the row space is 2. Okay, of course, just sort of to summarize here, the column space of a matrix is a subset of Cm, and the row space of a matrix is a subset of Cn. So as it turns out, these are hard to compare, but they actually, as we'll see soon, have some interesting common characteristics. Okay, here's an example. Let's go ahead and look at this coefficient matrix associated with archetype I, right? So we'll identify a linearly independent set T such that the span of T is equal to the row space of I. So we'll go ahead and just start with I transpose and apply theorem BCS to that. So I transpose, reduce to row echelon form. What we find is that I transpose in reduced row echelon form has 3 pivots. Those pivot columns are 1, 2, and 3. So we go back to I transpose and keep the first 3 columns as the basis of the column space of I transpose. Now, of course, that's the basis of the row space of I. Okay, so here are those three vectors corresponding to the reduced row echelon form of the matrix I transpose. Okay, so the row space of I is the span of this set T. Okay, and again here what we did is apply theorem BCS to I transpose. Here's an interesting fact, and I'll state this without proof, but it should be sort of intuitive. Suppose that A and B are row equivalent, then it turns out that the row space of A and the row space of B are the same. So to prove this, we'll have to use the definition of row equivalent matrices, right? Of course, matrices are row equivalent if you can get from one to another with a series of row operations. Okay, so as it turns out, those row operations don't change the row space. As an example of that, here are two matrices which we found way back when to be row equivalent. The row space of these matrices is the same. Okay, this sort of suggests an interesting approach to finding a row space, right? Since row operations don't change the row space, and since row operations sort of simplify rows, eliminating redundancies, it turns out that putting a matrix in its reduced row echelon form and then picking off the non-zero columns of the transpose gives us a set S that is linearly independent, and that the span of that set is the row space of the matrix. Okay, so sort of the take-home message here is that this is an alternate route to finding the row space of a matrix. Okay, that alternate route is to start with the matrix A, reduce it to its reduced row echelon form. Let's call that B. Now, of course, this reduced row echelon form of A will have 0 rows at the bottom. So when we take the transpose, of course, those 0 rows will become 0 columns. We'll keep all the non-zero columns, and it turns out that those columns are a linearly independent set such that the span of that set is the row space of the matrix. So here's an example as applied to the set T. So this set T is a set of 4 vectors with 5 elements, and we'll go ahead and think about the span of this set in terms of a row space instead of column space. Okay, here's a matrix A where I've just cooked up A by sticking the vectors from T as the rows of A, right? Then of course the span of T is the same as the row space of A. So I'll go ahead and apply this basis of row space theorem to this matrix A. Here's the matrix A, reduced to reduced row echelon form. We know that doing these row operations doesn't change the span of the rows. So here are 3 vectors such that these 3 vectors, when we put them back in columns, end up being a better description of the span of T. Okay, so here is that span. The set S is the set containing these column vectors we get from transposing the reduced row echelon form. And as it turns out, these 3 vectors are linearly independent, and they span the same space as the set T. Close with a theorem for you to work out on the worksheet. The column space of a matrix is the row space of a transpose. Not such a hard theorem, but I'll have you prove that on using the definition of row space. All right, folks, have a great day. Let me know if you have some questions. I hope you've enjoyed this video on column and row space. We'll see why these are like super important spaces coming soon. So take care. Bye-bye for now.